So this is lecture 9 on what I'll call the real simplex method, because what we looked at in the last talk was a simplex method geometrically for a linear programming problem with just two unknowns, two variables. But in general, you want to deal with more than two variables. When the geometric form, when you plot the feasible region, you go from corner vertex to corner point, doesn't work because you're in 3 dimensions or more. And I don't think we're ever going to look at problems in more than 3 dimensions or more than 3 variables. But for that, we need the real simplex method. And I'm going to start by doing a problem which is in the text, which is a standard problem. Only I'm going to set it up using the simplex method. So this is the problem that we've seen many times. If you're reading the book, you've read it many times. You have the Window Glass Company. And we have a problem which is to maximize the objective function 3x1 plus 5x2 subject to the following 3 constraints. X1 less than or equal to 4, 2x2 less than or equal to 12, 3x1 plus 2x2 less than or equal to 18, and the usual non-negativity constraints, x1 greater than or equal to 0, x2 greater than or equal to 0. So if we set up the feasible region for this, x1 less than or equal to 4 means we're in this strip between 0 and 4. 2x2 less than or equal to 12 means x2 is at most 6. So we're inside this rectangle. And 3x1 plus 2x2 equals 18. That's a line that looks like this. So for this problem, the feasible region is this, and the CPS, which is corner point feasible solutions. There's one here, 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 and here. This has coordinates 0, 0. This is 0, 6, 4, 0. This point is 4, 3. This point is 2, 6. And the way we solve this problem geometrically is we started at one of the corner point feasible solutions, 0, 0. Evaluated the objective function here, saw that we could get a larger value in either of these 2 directions, but larger if we go up. Evaluated the objective function here, got a larger value here, and that was the largest. So there's this geometrical process in 2 dimensions of going from corner point to corner point to corner point. CPF, corner point feasible. Now, in this formulation, we're dealing with inequalities. And when you have, but it's easier to deal with equalities. So we introduce what are called slack variables, because For example, to say x1 is less than or equal to 4 is exactly equivalent to, so in mathematics, this double-headed arrow means if and only if x1 plus x3 equals 4 for some x3 which is greater than or equal to 0. For example, if x1 is 1, let's say if x1 is 2.5, then if you let x3 be 1.5, you get x1 plus x3 is 4. If x1 is less than or equal to 4, x3, which is 4 minus x1, will be non-negative. And conversely, if x1 plus x3 equals 4 and x3 is greater than or equal to 0, then x1 is less than or equal to 4. So this x3 is called a slack variable, and it changes this inequality to this equality, to this equation. And we do that for all of the constraint inequalities. So instead of 2x2 less than or equal to 12, we introduce a variable, a new slack variable. So we have x1, x2, x3. Our new one we'll call x4. 2x2 plus x4 equals 12. x4 greater than or equal to 0. For the inequality 3x1 plus 2x2 less than or equal to 18, we introduce a fifth variable, 3x1 plus 2x2 plus x5 equals 18, x5 greater than or equal to 0. So this set of three equations with these 9 negativity conditions is equivalent to these three inequalities. So by introducing new variables, one variable for each inequality, we convert our inequalities to equations. So we can write our problem now like this. The problem is to maximize the objective function z equals 3x1 plus 5x2, subject to the following conditions. x1 plus x3 equals 4. I'm going to try and write these equations so the variables line up. 2x2 plus x4 equals 12. 3x1 plus 2x2 plus x5 equals 18. And the conditions that xj is greater than or equal to 0 for all j, 1, 2, 3, 4, and 5. So now we have equations instead of inequalities. Now we look for solutions of these equations. So we have 3 equations and 5 variables. If we assign values to 2 of the variables, then we end up with 3 equations and 3 variables. So there's generally a unique solution. If you have a solution x1, x2, x3, x4, x5, it's a feasible solution if all of the x's are greater than or equal to 0. It's not feasible if one of the x's or more is negative. And if one of the x's is 0, then this corresponds geometrically to being on the boundary of the feasible region. So when we have our linear programming problem and we introduce the slack variables to have equations, this is called the augmented form of the linear programming problem. And sometimes what we like to do is just rewrite the objective function. So let me just remember, the objective function is z is 3x1 plus 5x2. Let me just write this, I just bring everything over to the left. So this is the same as saying z minus 3x1 minus 5x2 equals 0. So I just set up everything as an equation with all the variables, including z on the left-hand side, and just some number on the right-hand side. So again, the first step in the simplex method is to introduce slack variables to change each inequality into an equality, into an equation, and also just to rewrite the objective function so it's in the form z minus whatever is the sum of the variables equals 0. And this is the augmented form of our linear programming problem. Now, how do we actually solve the problem? So our first step, the initial step or the initialization, is to set two variables equal to 0 and solve for the other three. And we always know that x1 equals 0, x2 equals 0 is a corner point feasible solution. So we start by choosing x1 equals 0 and x2 equals 0. And the variables you set equal to 0 are, so x1 and x2 are what are called the non-basic variables in this step. And the other variables, x3, x4, x5, are the basic variables. And we want to solve for x3, x4, x5. So if you look at the objective function, you see if you were to increase either x1 or x2, z would get larger. So this is not the optimal solution. This is not the best possible solution for the linear programming problem. And in fact, so we're going to change one of these. We're going to make one of these non-zero to increase the objective function. So we have to choose either x1 or x2. If we look at the objective function, when I've written it like this, the coefficients are -3 and -5. If you look at the negative coefficients, the one largest in absolute value is the coefficient of x2. And if you increase x2, you increase z. If you increase x1, you also increase z. But increasing x2 by a unit amount increases z by 5. Increasing x1 by a unit amount only increases z by 3. So you choose the non-basic variable, which gives you the largest possible increase in z. So our next step is, so this is the first iteration. We choose x2. So x2 will become a basic variable. And we'll choose another variable to become non-basic. When you choose x2, you want to make x2 as large as possible. But as large as possible, still within our constraints. So So let's look at the conditions on x2. x2 has to satisfy this equation. 2x2 plus x4 equals 12. And since all our variables have to be non-negative, we must have 2x2 less than or equal to 12, or x2 less than or equal to 6. So if we look at this second equation, the largest we can make x2 is 12 over 2, or 6. If we look at the third equation, 3x1 plus 2x2 plus x5 equals 18, x1 is equal to 0. We haven't changed that. So we must have x1 is 0, 2x2 less than or equal to 18, or x2 less than or equal to 9. So we're looking at this ratio. 12 over 2 is 6, 18 over 2 is 9. x2 has to be less than or equal to 6 and 9, which is the same as less than or equal to 6. So when you look at the ratio 12 over 2 and 18 over 2, the largest we can make x2 and still satisfy the non-negativity conditions is x2 equals 6. So let's see. If we let x2 equal 6, 2x2 is 12, x4 equals 0. So if x2 equals 6, then x4 is going to be equal to 0. So now we have two variables set equal to 0, x1 and x4. So what we see is in this first step, we have x1 equals 0 and x4 equals 0. These are the non-basic variables. And we have x3, x2, x3, and x5. x2 is equal to 6. What is x3? When x1 is 0, x3 is 4. When x1 is 0 and x2 is 6, this is 0 plus 12 plus x5 is 18. x5 is going to be equal to 6. So at this first iteration, if we look at, we have another solution to the set of equations. x1, x2, x3, x4, x5. Let me just write this as a vector. Is 0, x2 is 6, x3 is 4, x4 is 0, x5 is 6. So we have this solution to our system of equations. And they're all non-negative. And for this system of, for this solution, the system of values of the variables, what is z? Z, which is 3x1 plus 5x2. 3x1 is 0. 5x2 is 5 times 6 is 30. So let me write the equations again over here. So we have z minus 3x1 minus 5x2 equals 0. x1 plus x3 equals 4. 2x2 plus x4 equals 12. 3x1 plus 2x2 plus x5 equals 18 in the non-negativity conditions. So we start with the non-basic variables, x1 equals 0, x2 equals 0. And what are the values? So these are the non-basic. And these are the basic. When x1 and x2 are equal to 0, when x1 is 0, x3 is 4. When x2 is 0, x4 is 12. When x1 and x2 are 0, x5 is equal to 18. And also when x1 and x2 are equal to 0, z is equal to 0. Now, we want to get a larger value of the objective function by increasing one of the non-basic variables. And we see we get the larger increase if we increase x2. So we're going to change x2, make x2 some positive number. This is sometimes called the entering basic variable. So we want to change x2 to a basic variable. And when do we get, how large, and the larger we make x2, the larger z will be. So from this equation, x2 can be as large as the ratio 12/2. From this equation, x2 can be as large as the ratio 18/2. The smaller of those two ratios is x2 equal to 6. So we're going to have x1 is still 0, x2, x3, x4, x5. x2 is going to be a basic variable, and we're going to have x2 equal to 6. For x2 equal to 6, x4 is 0. So x4 is, well, it's called the leaving basic variable. It means it's no longer a basic variable. It's now going to be a non-basic variable. And I can solve for x3 and x5 to find out what they will be in this case. And one way I'm going to do it is just by simplifying these equations. So for example, I have x1 plus x3 equals 4. I don't need to change that. In the second equation, divide by 2, x2 plus a half x4 equals 6. So here it's clear when x4 is 0, x2 is 6. From here it's clear that when x1 is 0, x3 is 4. I want to eliminate the x2 from this equation. So I subtract equation 2 from equation 3. So this equation minus this equation is 3x1 minus x4 plus x5 equals 6. I took equation, if I just number these equations, 0, 1, 2, 3, to get from here to here, I took equation 3 minus equation 2. And in this equation, we see when x1 is 0 and x4 is 0, x5 is 6. And if I want to eliminate the x2 from here, I have to take this equation 0 and add 5/2 times equation 2. When I do that, I get z minus 3x1. 5/2 times x2 is minus 5, that cancels, plus 5/2 times x4. 5/2 of this oops, sorry. 5/2 of this is 30. So this is now my equation 0, equation 1, equation 2, and equation 3. I eliminated x2 from all the equations except the one where the minimum ratio was found. And we see when, for these values of the variables, z is equal to 30. So we got a larger value of z. Now, let me go back and look at my objective function. I still have a negative coefficient. If I increase x1, I increase z. So let's see if I can squeeze this all in at the bottom. How much can I increase x1? So let me just put a box around that. From this equation, x1 can be as large as 4 and x3 is 0. From this equation, x1 can be 3x1 can be as large as 6, or 6/3, x1 can be as large as 2. So here the minimum ratio I have, this is 1 times x1. 4/1, the right-hand side divided by the coefficient of x1. Here, 6/3. I have this ratio and this ratio. The smaller the minimum is 2. So I'm going to use this equation to pick a value for x1. And in fact, x1 so I'm not going to change x4. x4 is still 0, but I can let x1 equal to 2. And when x1 is equal to 2, x5 is equal to 0. And I need to find values for x2 and x3. So let me change this to a 1, and just using elementary row operations on equations, eliminate the x1s from this, everywhere else in that column. So I have 0, 1, 2, 3. So from this last equation, I want to have a 1 times x1, so I just multiply the equation by 1/3. I get x1 minus 1/3 x4 plus 1/3 x5 equals 2. And equation 2, I don't need to change. That is x2 plus 1/2 x4 equals 6. x4 is 0, so x2 is 6. In this equation, I take this equation and I subtract this equation from it. So I get x1 minus x1 is 0. 0 minus 0. x3 plus 1/3 x4 equals 4 minus 2 equals 2. Oops, I'm sorry. So it's this equation minus this equation minus 1/3 x5 equals 2. x4 and x5 are 0, x3 is equal to 2. If I add 3 times this equation to my objective function equation, I get z 0, x1, zero, it's easy enough just to add this equation to this. So I get z, this is 0, 5 halves minus 1 is 3/4 x4, x5 plus 0 plus x5. Yeah. And 6 plus 30 is 36. So if you look at what we have for this choice of variables, 26200, z is equal to 36. And x4 and x5 are 0. Any increase in the variable x4 or x5 would decrease z. So there's no way I can increase one of these variables and get a larger value for the objective function. So we're done. The maximum value is z equal to 36 when x1 equals 2 and x2 equals 6. So this is the algebra of the simplex method. Now I'm going to make this a little bit simpler by converting this to what is called tableau form. So what I just talked about in the text is section 4.3, but what will be the algorithm that'd be easiest for you to use and solve problems by hand, section 4.4, which is the simplex method in tabular form. That is, we make a table. And this was our initial augmented form of the problem. We take our inequalities, add slack variables to get equalities, write the objective function as z minus something equals 0. And from this, I'm going to make the following table. So this will be equation 0, 1, 2, and 3. And our variables are z, x1, x2, x3, x4, x5. And then on the right-hand side, we have a number. And what I'm going to write in this table are the coefficients of these variables in these equations. So for example, z minus 3x1 minus 5x2, this is 1 times z. Make z of this one, 1 times z minus 3 minus 5, 0, 0, 0 equals 0. Our second equation is x1 plus 3 equals 4. The coefficient of x1 and of x3 is 1. The coefficients of x2, x4, and x5 are 0. And the right side is a 4. For the equation 2x2 plus x4 equals 12, the coefficients, these are all 0. There's no z. 0x1, 2x2, 0x3, 1x4, 0x5 equals 12. And for the last equation, it's 3x1, 2x2, 0x3, 0x4, 1x5 equals 18. So this is the table. And how do we solve the problem, the linear programming problem, using the table? So as before, we want to decide which of our variables will give us the greatest increase in z if we increase the variable, and that's x2. So, because 5 is bigger than 3. So this is the column of coefficients for x2. 0, there's no x2 there. We don't have to worry about that. In this, 2x2 is at most 12. 12 over 2, that ratio is 6. For this, the largest x2 can be is the ratio 18 over 2, which is 9. And this is the minimum. So we're going to let x2 equal 6 and x4 be equal to 0. So this is the row in which you have the minimum ratio of right side to coefficient of the variable. And what I want to do is in this column, using elementary row operations, you can multiply an equation by a constant. You can add or subtract a multiple of one equation to another. I want this to be a 1 and these to be zeros. So let me set up my next table. That's what it looks like. And this will be equation 0, 1, 2, 3. So in equation 2, I multiply by a half. So I get 0, 1, 0, a half, 0, 6. And then I want to get a 0 here in row 3. I could just take this row minus that row. 0 minus 0 is 0. 3 minus 0 is 3. 2 minus 2 is 0. 0 minus 0, 0 minus 1, 1 minus 0, 18 minus 12. I already have a 0. 0, 1, 0, 1, 0, 0, 4. And I want to get a 0 here. So I multiply. I can multiply this row by 5 and add to this row. So 0, minus 3 is minus 3. 5 minus 5 is 0. 0 and 0. 5 halves. 0. 5 halves of 6. I'm sorry, 5. 5, 5, 6 is 30. So this is my new table. This is still 1. Now in this table, I look and see in my 0, do I have a negative coefficient? Yes, minus 3. So zero, 1, 2, 3. I'm going to now work with the variable x1. For the variable x1, if I look at the ratio, 4 over 1 is 4. 6 over 3 is 2. This is the minimum. So the most I can increase the variable x1 by is 2. So no, I want a 1 here and zeros above it. So I can take this row and multiply by a third. I get 0, 1, 0, 0, minus a third, 2. I already have a 0 there, 0, 0, 1, 0, a half, 0, 6. To get a 0 here, I can take this row minus this row. 0 minus 0, 1 minus 1, 0 minus 0, 1 minus 0, 0 minus minus a third, 0 minus a third, 4 minus 2. So I get 0, 0, 1, a third minus a third, 2. This all looks good. And finally, I want to get a 0 here. So I just add this row to this row. That gives me 1, 0, 0, 0, 3 halves, 1/3, 36. And now there's no negative number in this 0 equation, in the z equation. That means I've reached my maximum. What are the values of the variables? Z you have 36. It says let me just go back one step and indicate in each of these tables which are the basic variables. So z, x1 is 0, x3, x2 is 0, that's x4, x1 and x2 are 0, x5. So now we have x2 is 0 and x4 is 0. sorry, x1 is 0 and x4 is 0. So we have a value x3, x2, and x5. And in our last table, we had x1 and x4 as the non-basic variables. So x1 and x4, so x3, x2, and x5. So in the last step, our basic variables will be x1, x2, x3. x4 and x5 are 0. And we have the values x1 equals 2, x2 equals 6. Sorry, x3 equals 2, x2 equals 6, and x1 equals 2. And when x1 is 2 and x2 is 6, we get the optimal solution. So this is a little bit more complicated than I would like. And in the next talk, which I will post very soon, I'll do another problem using this tabular method. And the more problems you see, the easier it becomes. But it takes a lot of work to understand what's going on. And you have to read the book carefully and spend a lot of time with it. That's it.